All right, welcome everybody. Thanks for coming out. My name's Mike Muglia. I'm a scientist here at CSI. Can you hear me all right? You need more volume? It's okay? Okay. I think I'm just going to introduce myself this evening. I'm a pretty informal guy. I put on my nice dress for this talk. I have my leather flip-flops on. So I'd like this to be a rather informal talk, and I want everyone to feel comfortable and also be involved a little bit. And Ryan's asked that I ask you to hold your questions till the end, and the reason for that is so that we can pass a mic around and our online audience can hear your questions. However, Ryan's not going to like this. If I say something that you're absolutely befuddled about, it probably would help our online audience to have you bring it up. So please just interject at any time. Tonight I'm going to talk about peaches and stream. So as scientists, we actually have competitions to see who can come up with the best acronyms. And my friend Dana down at Skidaway Institute of Oceanography came up with the PEACH part. The PEACH stands for Processes of Exchange at Cape Hatteras. And of course, Dana's from Georgia, so she did really well with that one. And then, of course, the stream is the Gulf Stream, which plays a huge role in those exchange processes. So it's a big body of water, and I'll talk a little bit about that. The projects have been funded by the National Science Foundation, the PEACH project, and by our Ocean Energy program here at the Coastal Studies Institute. So a lot of the observations that I'll show you were generously provided by both of those programs. Okay, so let's get started. What I'm going to tell you about is how does the ocean move off of North Carolina? So specifically, what's going on in your backyard, and how do we know that? I'm a scientist. I'm not going to say you got to believe me. I'm going to say I'm going to show you what I measured, and I'm going to show you how I measure it. And then finally, as an Outer Banks person, how does that affect me? Why do I care? And I'll give you some examples. So we're going to start by talking about how the ocean moves off of North Carolina. North Carolina is a fascinating place. So that's the reason that the oceanographers for the PEACH project, they're from Woods Hole all the way down to Georgia, and everyone's focused on North Carolina. And the reason is that the oceanography out here is very special. So to get you oriented a little bit, here's North Carolina, here's Duck, Cape Hatteras, and Cape Lookout. And I've highlighted a lot of the major bodies of water here, and as a physical oceanographer, we identify these bodies of water often by the salinity or temperature of that water mass. So one of the major water masses here is called the Mid-Atlantic Bight shelf water. So on the shelf, we're usually inside of 100 meters, so the inshore water. And this water typically flows from north to south. We don't really call this a current because it doesn't consistently move that way, just on average. And so that means if a cold front comes offshore, it might switch with the wind, right? So this Mid-Atlantic Bight water is called the cold pool, and that's because it's cold. It's coming from up north. It's a mixture of many different water masses. South of Cape Hatteras, we have the shelf water from the South Atlantic Bight. That water is warmer and it's saltier. And so those two water masses tend to meet here off of Cape Hatteras in what's known as the Hatteras Front. And if you've seen oil and water before, different density fluids don't typically just mix very well. There is some mixing, but they don't readily mix. And so they form a front, a lot like a front that you see on a weather map for the same reasons. We also have what's called the shelf break front, because here at the shelf break, we have the slope sea, and this recirculation just for cartoon purposes is here, but really this ranges in a big recirculation off to the northeast. And that water has its own temperature and salinity. And there's a front there where it meets the Mid-Atlantic Bight cold pool water. And then, of course, as most of you probably know, offshore we have the Gulf Stream. And the Gulf Stream is really warm and salty water. And it's a massive flow. And we'll talk a little bit more about that. So, again, I don't want you to just believe me because I tell you so. I'm going to give you an example of a measurement that shows some of these different water masses. This is called, this is a satellite sea surface temperature image. So what you're looking at is just the surface water temperatures. And I have a color bar here so you can tell this hot water, the hotter colors are the Gulf Stream. This cool blue water are the cool waters of the Mid-Atlantic Bight. And when I overlay that, you start to see some of these features that I mentioned here. So you can see that there is a front between these two water masses in the South Atlantic Bight and the Mid-Atlantic Bight. There's a front here on the Gulf Stream. There's these big meanders that are very typical of this area. And there's a warm water filament, and these filaments tend to get sheared off of this inshore edge of the Gulf Stream, and some of that water can get pushed up on the shelf here. So there's a lot going on here. There's a big recirculation here in the slope sea, and a lot of times these what we call cold core rings will break off of the Gulf Stream, and we'll have almost like a low pressure in a weather map that you see spinning in the ocean there for long periods of time, for months. So it's important also that you realize that this is a very dynamic system. So I can show you stills of it, but this is the Gulf Stream and all those water masses in motion. So what you're looking at here is actually model data from what's called the HICOM North Atlantic model. And you can see we're going to loop through a whole year of looking at these different sea surface temperatures and how they change. And you see a lot of different features in this loop. When it's summertime, you don't see a big temperature gradient between the Gulf Stream and the South Atlantic Bight water. Now, as we get into the winter, you start to see that Hatteras front right in here is very prominent, right? And it moves around, and it's forced by winds. So when a cold front comes off, when a low pressure moves off, it tends to push that front around. You also notice that I've got some highlighted lines on here. The white lines, or hashes rather, are kind of the long-term average position of the stream. And so when you can see the Gulf Stream wiggling around, we like to say that it's like a garden hose. And the reason that that's a good analogy is that the Gulf Stream at some latitude is, the flow is relatively consistent. So like a garden hose, if you have flow through a hose, you can move that hose around, but the flow through the hose tends to be about the same. And so the stream does that. And this is the long-term average position of the stream. This is the 100-meter isobath, and that kind of delineates the shelf water from the deeper ocean water. And then these three transects here are specific transects that are interesting to our ocean energy program. We're looking at whether the Gulf Stream can provide energy to the state of North Carolina. So those are kind of our research focus locations. So also, we can't just focus on surface. All I've shown you so far is the surface, sea surface temperatures, right? Let's take a look down below the surface and see what's going on off of Cape Hatteras, because there's a lot of interesting behavior going on below the surface as well. So what we're going to do is we're going to take a slice here of the Gulf Stream. And so we're going, here again are some different, we call these isobaths, or equal depth. We're going to go off of the continental shelf, where it's relatively shallow, into the deeper water and take a slice through it and see what it looks like. So this is a cartoon that represents a slice of the Gulf Stream. So here's the shore, here's that cooler Mid-Atlantic Bight water, and the Gulf Stream is what we call a baroclinic jet. And it's a very deep body of warm water. And what's shown here in the picture is this is the cross-stream section that I was pointing at from the last figure, and these are called isotachs, and that's equal speeds. And so if you've ever been offshore, you notice that the Gulf Stream water is flowing pretty quickly. In the jet, this area right here, down to about 100 meters, the currents can be about 2 meters per second, or maybe 4 or 5 knots, which is a huge current for an open ocean current. And off of Cape Hatteras, the Gulf Stream is roughly 1,000 meters deep. And so that depends how you define it, and I'll talk a little bit more about that. But what's interesting is that if you have this deep, warm jet of water, the warmer water is not as dense as the colder water around it. And so you have to have something force that jet to make it sit down in the water like that. It's like oil and water. If you push the water down and oil down deep into the water, it doesn't want to do this like a bowl. It wants to lay like this, right? So the winds are forcing this Gulf Stream jet to be like that, And there's a tremendous amount of energy, potential energy, in that baroclinic jet. And what that means is that that jet wants to do this all the time. And if it does this just a little bit, it gives up some of that potential energy, and that can go into energy of translation. So you see the Gulf Stream do a little bit of this, right? So same concept. We're looking at this cross Gulf Stream section here, but we're going to go even deeper. So what I'm showing you here on the left, these now are called isotherms. So these are equal temperature lines or curves. And the Gulf Stream water is down to about 1,000 meters. And again, it's very important that we say the Gulf Stream is here based on some definition. So we could say, well, the 5-degree isotherm represents our Gulf Stream down to 1,000 meters, let's say. But what's really interesting is if we go below the stream, there's this tongue right here of Antarctic Intermediate water. And so this water is flowing like the stream to the north. This water is flowing to the north, coming all the way up from Antarctica. This is upper Labrador Sea water. So this came from the Labrador Sea way up north, and it's flowing south. And then this is deep western boundary current water down here. And this water is also flowing south, and this water originated by newly formed bottom water in the North Atlantic Ocean. So it was dense enough, and it sank, and it came all the way down the shelf break, and it's going underneath the Gulf Stream at Cape Hatteras. I'm also showing here some measurements that we've made that show the current speeds. And so these hot colors right here are the speeds above 1 meter per second, and this is the Gulf Stream itself. This is the jet, and we've highlighted these colors that are in an opposite direction. So this is that body of water right there, the upper Labrador Sea water flowing the opposite direction. So this would be like into the page, and this would be out of the page, which is really interesting. One thing I need to point out here is that it looks like if I were walking along the continental shelf here and I got to the transect that I'm talking about, that I would hit this cliff, and if I could just walk off, I would fall down a cliff, right? And that's just because of the scale. So what we've done is kind of scrunched it together so that you can see all of these things, and the slope is not nearly this steep. It's exaggerated here. So if I were driving a boat across this area right here, I would see a quick and noticeable difference in the bottom, but it's not like a cliff, okay? All right, so how do we know all these things? How do we measure it? That reminds me, let me back up just one slide. One thing that's very interesting is you notice that we have the Gulf Stream water here, and then we have this upper Labrador Sea water, but I didn't say anything about this tongue of Antarctic Intermediate water. And that's because it's kind of moving in the same direction as the stream, so when I measure the current speeds, I don't really see it as being different from the stream. The way this body of water has been identified historically is by the high silicates that are in it. So the Southern Ocean around Antarctica has a lot of very high silicates, and that's the only place in the world that you'll find siliceous sponges. So they look like a sponge that you're probably familiar with that you can squeeze and is soft and sometimes gets used in the shower, except they look more like blown glass. So they're very beautiful, and they can get silicates from the ocean water cheap, and that's why they make their skeletons out of silicates. And when I say cheap, I don't mean they're trading in silicates down there. I mean that energy-wise, they don't have to invest a lot to take it out of the water and build their skeleton out of it. All right, so how do we know all these things? What are we doing to measure all these different parameters in the ocean? I'm going to highlight some of our main instruments that we use in the projects that I've shown you, and I'll tell you a little bit about them and how they work, and I've brought some in to show you. First of all, let me point out how comprehensive our array of measurements are right now for these two programs that I mentioned. We have moorings along the shelf. These are in 100 meters of water, and each one of these three has a 300 kilohertz ADCP in it, which I'll talk about in a moment. We have moorings here at these green dots, and each one of these has 150 kilohertz ADCP in it, and these are going to be deployed for 18 months. They're out there now, actually. So as oceanographers, we like that because that means when we're going to have a beer, we know that we're working anyways, right? We're collecting information. These red lines are transects that we made in a big research vessel, and we used ADCPs to measure currents. We used CTDs, which I'll also talk about, to measure the salinity and the temperature of the water beneath the vessel. And then we have a big network of land-based coastal ocean radars that measure surface currents on the ocean. And they make measurements about every half hour, every hour, and I'll show you some of them. So all these things right now, after I'm done talking to you and I go have a beer, I'll be working hard because I'll all be collecting information. All right, this is an example of all the different things we do with an ADCP. So an acoustic Doppler current profiler is known as the workhorse of physical oceanography. In fact, this instrument right here is an ADCP, and it's called a workhorse. And it is a 300 kilohertz ADCP, and these four things here are a lot like fish finders. They send a sound up in the water column, or down in the water column, or sideways in the water column, however I choose to point it, and they measure the current above these heads. And the 300 kilohertz ADCP can measure a column of water about 100 meters deep. So that means typically we'll say every meter I look at what the current velocity is doing, all the way up 100 meters. And so we can take this instrument and we can deploy it a number of different ways to do that. So here's an example of a 300 kilohertz ADCP being deployed on a pod that will sit there for 9 months. And that means at one place I have consistent measurements of the current over nearly 100 meters of water, meaning every 10 minutes I'm making a measurement. And I know what's going on at that one place with consistency from this instrument. I can take the instrument and I can put it on a boom, and I can look down, and I can drive across some body of water, and I can get a snapshot of what the current's doing below the boat, 100 meters down when I do that. I can put one of these instruments in a buoy, there's one right there, and I can deploy it, and I can sink that buoy down underwater, and I can look up 100 meters in maybe this buoy, for example, was deployed in 300 meters of water, and I can look up and see what the top 100 meters of water is doing in terms of currents. And this brings up a good point in that there are trade-offs with the frequency that you use. So typically, a lower frequency instrument will get more distance with less resolution. So I choose which frequency I'd like based on what question I'm trying to answer. So this will measure 100 meters distance and 1 meter resolution, let's say. I can put out 150 kilohertz ADCP and I can look over a 300 meter water column, but I can only get 4 meter resolution. So this is a picture of our new research vessel, and it has 2 ADCPs in it that we can use to drive across the Gulf Stream and measure currents below it. It has a 75 kilohertz and a 300 kilohertz. And what that does is it gives us high resolution near the surface, but lots of distance, so we can see way down like 400 or 500 meters. And this is an example of what we can do with a vessel-mounted ADCP. So what we're doing here is we're driving from about 100 meters all the way across the Gulf Stream, and the ADCPs are showing us, here these hot colors are the high currents of the Gulf Stream, and here's the upper Labrador Sea water, and they're looking with acoustics and measuring a snapshot in time of what the current's doing. The other workhorse of the physical oceanographic community is called a CTD, and there's a CTD here and a CTD here on one of our moorings. And that measures conductivity, temperature, and depth. And the conductivity tells us what the salinity of the seawater is. And so with those 3 parameters, we have a good idea of what the density is. So then we get to understand these different fronts. We can identify, well, we're in the mid-Atlantic Bight water right now, and we're in the South Atlantic Bight. No, this is Gulf Stream water based on those parameters. And like the ADCP, we can do a lot of different things with a CTD. In this case, we have a CTD on what's known as a rosette. And we'll take this, we took this one on a big ocean ship, and we lower it down to the bottom of the ocean like 3,000 or 4,000 meters in the water column. And if someone's interested in a certain salinity or temperature water mass, we can snap one of these bottles shut while we're at that depth when we measure it with the CTD, and we have a sample of that water to do whatever we want with it. Also, we will deploy them on our moorings. Here's an example of one with an 80 CP mooring, and we can put that on the bottom, and we can measure for a whole year what water masses are moving over that mooring while we're measuring the currents. And so here's a couple of neat examples. Remember, we're really interested in what's going on off of Cape Hatteras. So when we do a CTD cast from that big ship, we drove across the stream here, and right here in the middle of the Gulf Stream, we said, let's drop that CTD down all the way to the bottom. And you can see in both the temperature profile as we go down with depth and the salinity profile where the Gulf Stream is, right? It matches up pretty well with those high currents. So that's an example of what we can do with a CTD cast. This other picture is, this is temperature and this is salinity. And what we did is we took a CTD much like this one and we put it on a pod, and it just sat there for 9 months, and it measured what the temperature of the water was and what the salinity was while it was down there. And I've grouped these water masses that it sees based on that temperature and salinity, and I've said, look, sometimes it had the Gulf Stream water over that pod that we put on the bottom. And at other times, it had the South Atlantic Bight winter water or upper slope water over the pod. And then at other times, it had the Mid-Atlantic Bight winter water over the pod. And this helps us start to piece that puzzle together of how these different currents are moving over that pod that I put on the bottom. Another neat toy that we have for making casts on outboards when we don't have a nice rosette is we put a CTD on a fishing rod and we lower it down about 100 meters and we get a nice cast. And this is an efficient way for us to take the outboard out, measure currents, and get a few CTD casts as we do it. All right, we also use HF radars, and this is a really neat HF radar site that we put in the core banks of North Carolina. And these guys were instrumental in doing it. These are my friends Ryan and Tony, and this is my boss Harvey. And this site is completely powered by wind and solar power because, as you probably know, if you're Outer Banks folks, the core banks are rather remote and power sources are pretty scarce. So this thing runs, gives us a picture of the ocean currents every hour. This is an example of one of the radar antennas. This is the one that lives down in Buxton, North Carolina. And these are the kind of images that we get. So on the left here, we have the surface currents. This is like the top 2 to 3 meters of the water. The hot colors are the faster currents, and the cooler colors are the slower currents. There's a network of these land-based HF radars all the way up the northeast coast. And we get a picture like this every hour. So remember I said that was an atypical sea surface temperature picture from the satellite in the beginning? When it's cloudy, we don't see anything, and that can happen for weeks. These guys don't care if it's cloudy. I can tell where the edge of the Gulf Stream is pretty easily with these HF radars, every hour with consistency. So that's a valuable tool. This is a 5 megahertz radar, so it has about 6 square kilometer resolution. This is a higher frequency radar. This is 13 megahertz, and what you notice when you look at these two is that I get a lot more measurements, like 1 every kilometer instead of 1 every 6 kilometers. So what we've done is we've embedded for this Peach project a network of higher frequency radars within our network of lower frequency radars for that experiment. And then we get both. Again, when I lower the frequency, I get a lot more distance, but less resolution. And then finally, these are the newest, greatest thing for oceanographers. These are called gliders. And these are pretty neat because ship time is very expensive. So if I want to go out on a research vessel like the one I showed, I'm spending $30,000 a day to make these measurements, right? One of these costs $160,000, and if I take good care of it, it'll last for years, and I can put ADCPs on it, I can put CTDs on it, and I can fly it around, and it can collect those measurements, and then when it comes to the surface, it can transmit all those measurements via satellite back to me at my desk. And I can tell it, I want you to change and go over there, there's a hurricane, and it'll go back underwater. Now, how does this thing get drive? How does it have energy to do that? It's pretty neat. This is us launching one, Steve and Tripp are in the audience, about a week ago. And this thing will go overboard, this polyball won't be on it. It'll be by itself, and it changes its buoyancy. So as it starts to sink, those wings give it forward thrust. And it flies down and has altimeter, and it says, ooh, I'm getting awful close to the bottom, I'm going to be more buoyant. And it turns like this, and then it flies up towards the surface. It transmits its data, gets new instructions from Steve, starts back down again. And it flies around like that, and we measure salinity, temperature, chlorophyll, currents, whatever package you want to put on that. So right now for our Peach project, we're flying 2 of these like the yellow ones, one north of Cape Hatteras and one south of Cape Hatteras in the shallow water. And then we have these red ones that are called spray gliders, and they tend to fly in much deeper water, and we are putting them in Miami, and they're flying back and forth across the Gulf Stream all the way up here. So you say, that's great, that sounds really cool, but how does that affect me, right? Why do I care about that stuff? Well, I'm assuming that many of you guys are Outer Banks folks, and that means that you love the ocean. I have met some people that are an exception, but for the most part, there are 3 different types of people that love the ocean out here. There are your beachgoers. So I'll give you an example of beachgoers here.
These people are swimming in their shark-proof cages. They don't want to get eaten. Get some fun.
All right, so if you're a beachgoer and you like to go swimming in Kill Devil Hills, and you, as you guys now know, the Mid-Atlantic Bight cold pool is in Kill Devil Hills, and it might be in August, and you go swimming, whoops, forgot to click on it, sorry about that. If the wind's been blowing out of the south-southwest or along shore, what that tends to do is it pushes the surface water along the beach, along shore, and the earth rotates, and most of that water moves offshore, and it doesn't look like an extreme low tide with no water at the beach. There's water there. The water that's there is the water that comes up to replace it from down below. And in Kill Devil Hills, typically that water is the Mid-Atlantic Bight cold pool water, and as most of you probably know, if it blows southwest for a week in Kill Devil Hills, the water might get into the 50s. It's cold, right? But interestingly enough, if I'm down here in Frisco and I get upwelling favorable winds, it might cool off a little bit, but I'm not going to go put on booties in a wetsuit. It just doesn't get that cold. And why is that? Because the water that's being upwelled is this warm South Atlantic Bight water, typically, right? So it's not as cold. It's not uncomfortably cold. So that's why this is such a neat place. There's some neat dynamics here. So if you're a beachgoer, now you understand, that if it's been blowing southwest for a week, you might want to go down to Ocracoke or Frisco to go swimming, right? Well, now if you're a surfer, like this guy,
It's just like, dude, you get the best barrels ever, dude. Just like you pull in and you just get spit right out of them. And you just drop in and just smack the lid, whoop, drop down, smack the lid. And then after that, you just drop in, just ride the barrel and get pitted. So cool like that.
all right, so I have a bunch of friends like this guy. I see some in the audience. In fact, I could be this guy, I'll admit, all right? I'm like that guy. So I happen to like to surf down at the lighthouse, especially in the wintertime. And there's this wild thing that happens down at the lighthouse in the wintertime. I can go down there, and I've been wearing a hood, boots, gloves. The water's 45 degrees here, and I can go down there in January. And all of a sudden, I find out that, I did it again, that the water is 60 degrees. And that's because that Hatteras front, for some reason, it's been blowing south for a long time, and there's a big south swell coming, and it has pushed that front way up north. And I'm surfing in 60-degree water in January, and that's why, because that front's been pushed way up north. All right, and we all know if you're not a beach goer, you're not a surfer, maybe you're a fisherman. We have a popular place for fishing, right? So one place that I'm pointing out here is known as the Point. It is this little, it's more like up in here, but the little dimple in the bathymetry here is a very productive area. So if you're fishing out at the Point, you might have something like, uh-oh, I got an ad. Bear with me. It happens to the best of us here.
Peace with Soda's Cool to the Touch memory foam. The all-new Serta iComfort Temp Touch mattress collection. Experience it only at Mattress Firm.
Did you catch one of those?
Oh no. Damn. Did you see that?
All right, so why is the Point so productive? Well, remember these big meander rings in the Gulf Stream. When the Gulf Stream peels away from the Point, the Point is like a big canyon in the shelf slope. When it peels away from the Point, you're taking a huge quantity of water and you're moving it offshore. And there's not a big hole where you can look down and be like, there's a canyon, right? That water has to be replaced, and it's replaced with upwelled water that comes up that canyon. And that water is rich in nutrients. And so when you take all these nutrients and put them up to the surface where plankton can utilize them because they have sunlight, they bloom, and then the little critters eat the plankton, and then the big fish come in, and then you have good tuna fishing at the Point. So to try to communicate how much water that is when the stream moves around, off of Cape Hatteras here, the volume of water moving in the Gulf Stream is probably 40 times the volume of all the rivers in the world combined. So a friend of mine, Roy Ying, who's an oceanographer at NC State, explained to me when he was working on the South Atlantic Bight, if you take the Gulf Stream and it's laid up against the shelf break here and you move it offshore, you move so much water offshore that if you don't fill it with something, you could drain the entire shelf into that hole. Like, that's how much water it is. So that's why there's an enormous amount of water that has to come up to replace it, and it brings all those nutrients up. All right, so I'm going to take some questions, but first I want to let you all know that a lot of what I've talked to you about is made from the contribution of a lot of very special people. So I put a lot of my colleagues on here. Steve is in the audience. Ryan and Tony are down at the Institute for Marine Science at UNC. Tripp is a technician here. And these are all the principal investigators on the National Science Foundation Peach project that I talked about. So these are all my colleagues, and this is on the big research vessel. Nick is another technician here who's instrumental in working with us. It takes a lot of good people and a lot of hard work to collect those observations, and they're very valuable people. The other thing that's interesting about these projects is that all these folks are from different institutions. We have folks from NC State, we have folks from Woods Hole, Skidaway Institute of Oceanography, folks from the University of North Carolina at Chapel Hill, folks from ECU, and it's a very big collaboration between a lot of different people, and that's what makes it a valuable and exciting collaboration and so productive, I think. So, without further ado, we should have some discussion, I think, some questions. And here comes Tripp with the microphone. If you have a question, if you raise your hand, we can bring you the microphone so that the folks online can hear you. Ellie, do you have a question? All right, Tripp's bringing you the microphone.
Where's the beach ball?
Oh, I think Tripp can answer that question for you.
It is currently in my office.
Speak into the microphone.
Where's the beach ball?
Okay, the beach ball is in Tripp's office. So we were working offshore last week, and Nick looks out the side window and he says, "What is that? Hand me the binoculars." And he looks out, and there's a beach ball that's about 7 feet in diameter, rolling along. So we had to have it, so we got it, and Ellie got to play with it, and then we put it in Reed's office, and then he couldn't get in his office, and now it's in Tripp's office. All right, any other questions?
I know that the South Atlantic Bight goes from Cape Canaveral to Cape Hatteras, right? The Mid-Atlantic Bight goes from Cape Hatteras to where?
To, so again, a matter of definition, but about Massachusetts, right? So once you come around Cape Cod, you're in the Mid-Atlantic Bight, I think. And so it's interesting, a lot of the water that's on the Mid-Atlantic Bight is from outflow from like the Delaware River, from the Chesapeake Bay, some water that comes around from the Labrador, big mix.
Okay, so you have all this data on currents, and I was wondering if you could tell us if the Gulf Stream is a sustainable source of energy for North Carolina, and when will we begin to harvest it, if it is?
We don't know yet if it's a sustainable source of energy. We're studying that. So the key to getting energy from the Gulf Stream isn't that the stream flows and slows down a lot. It's always flowing a lot. It's not always flowing a lot in the same place. So if you want to continuously get energy from the Gulf Stream, you have to follow it as it moves. And so we're working on that. And so a lot of the information that we gather is to try to find out if it is a viable source of energy, and I don't think we have an answer to that yet. We have a lot of information and we're getting there. Part of it is finding the sweet spot. So if I don't move with it and I pick a place that I have to put an underwater turbine, for all these different practical reasons, where's the best place? In terms of how long it's going to be until we can get Gulf Stream energy, that is a question that I think is a political question. So what that means is if we had the political will to say we absolutely have to have energy from the Gulf Stream, then it shortens the time period, right? But if it's not there, then the funding's not there to go after it, develop the technology and everything. So it's more of a political question, right?
So there's all these eddies that spin off from the Gulf Stream, usually after it passes Hatteras, right? There's some work that's been done by some geologists looking at sort of historic, meaning thousands of years ago in this case, that suggests that Pamlico Sound was salty sometime in our geologic past. And they base that on what they suggest are filaments that are coming off the Gulf Stream. So warm water moving into the Gulf Stream, warm salty water moving into Pamlico Sound. And I'm curious if you see something like these, for lack of a better word, filaments or something that come off from the Gulf Stream around sort of Onslow Bay area that move actually towards shore.
Yeah, actually, I thought I pointed one out earlier, but this is an example of one of those filaments. And this is some stream water making its way up onto the shelf. And so if your Barrier Island was more permeable at one point in time, these filaments could easily move a lot of water up and into the Pamlico Sound regularly. Yeah, so what's not sound, though, what's important is that these filaments can move water onto the shelf, and they do. And so when people talk about, again, Buxton being 60 degrees, they like to say it's Gulf Stream water. Well, the Gulf Stream is Fahrenheit in the 76, 78. But is some Gulf Stream water mixed in there and getting there? Yes. What's not sound is the Gulf Stream doesn't come up here on the shelf. It's 100 meters deep here, and the Gulf Stream is in a 1,000-meter baroclinic jet. The physics are not sound to have the Gulf Stream move up onto the shelf. And the reason for that is what we call is a vorticity argument. So in the deep ocean, there's a spin related to a water mass. And that spin is almost perfectly conserved in the deep ocean, meaning in 4,000 meters of water, if I have a current going this way and there's a seamount, that current won't go over the seamount, it will go around it. And the reason for that is it's not physical for all this water that's next to each other to have some spin, and like an ice skater, all of a sudden you squash all that water and it slows down a whole lot when all the other water is spinning around it at some vorticity, we call it. So that's why the Gulf Stream has a potential vorticity and some spin, and it's not going to go up onto the shelf where it has to get squashed from 1,000 to 100 meters and slow down with that spin. It's a short answer. Long answer.
Do you think that commercial and charter fishermen know what you know intuitively, number one? And then number two, is it possible that your information, because you have such immediate data, would be helpful to them? And is that a possibility, or not? Maybe not especially.
That's a terrific question. In fact, when we started with this NSF work, I was very eager to bring a lot of the fishermen in to be involved with it. And for budget reasons, we did not do that, but we're still considering how we might get funding to do that. I think that the fishermen in this area, commercial and charter fishermen, probably know a heck of a lot more than I do about what's going on out here, what this Hatteras front does. And what we'd like to know here is that because there's this pressure gradient, this is almost like a step. When I say pressure gradient, I mean like the water surface is tilted because one's warm and one's cool. And so what a pressure gradient does is it drives a current. It's like if you slop water in a bucket, right? It goes up on the side, but it doesn't sit there. It wants to correct that. And it's the same thing in the ocean. If you have some slant, it wants to kind of try to correct that. So we hypothesize that there's a cross isobath current that goes along this front. And how that moves could be very important to biology moving back and forth, because a lot of currents don't go across isobath. For that same vorticity reason, they like to move in the same direction as the depth. So it's a special place for that reason. So I think that they understand probably the biology here much, much better than we do. I've had conversations with them about the Gulf Stream and the Point, and they know a heck of a lot about what's going on out there, and it's valuable information. In terms of the information we gather and would it be valuable to them, we've actually done workshops with those coastal ocean radar surface currents to say, hey guys, look, you're always looking at sea surface temperatures. When it's cloudy, you don't get anything. You can get these every hour. So if you're trying to find the edge of the Gulf Stream and you don't have any satellite data, look here, right? So that could be, more of that could be done, but I think that's valuable information. I've had some guys call me up that are friends of mine and say, hey, I got a tournament coming up. Can we sit down and go over, what you think the stream's doing? So I've fished myself based on those radar currents. In fact, we wrote a proposal, a commercial fisherman and I, to try to go fish based on those radar currents alone. Allie, why don't you let everybody have a chance, and then if nobody else has questions, you can ask some more. Anybody else have more questions? These are great questions, Bill.
Will sea level rise affect at all the position of these streams? Will they move westward, or are they constant within reason?
That's a great question, and a lot of it's not so much sea level rise affecting stream position as it is climate change potentially affecting Atlantic, what we call Atlantic meridional overturning. So the Gulf Stream is a big part of a big cycle. And so I mentioned there's a lot of bottom water that's formed in the North Atlantic. It's a very special place for that reason. That water sinks and moves south. The Gulf Stream is bringing volume of water and heat back north. And so the reason that the water in the North Atlantic sinks is that it's dense enough to sink. And that means that it's cold enough and it's salty enough. And so some scientists have hypothesized that if all the glaciers melt up there and the salinity drops, that it won't be dense enough to do that anymore, right? Now that's a big assertion. I'm not making that assertion. But when you slow that system down, you could slow down the flow of the stream. Now, in terms of that, it has been shown on shorter time scales that the stream is based on what we call the wind stress. So that whole stream is forced by the winds over the North Atlantic. When the wind stress slows down, the stream flow through the Florida Strait slows down, and that has a lot to do with how the Gulf Stream behaves dynamically. So I can't remember what it is, but if the volume transport is less, I think that it tends to not meander offshore as much, but I might be wrong. So that matters. So it is all linked. Also, in terms of water levels at the beach. It's very difficult to tease this out, but some scientists have said that the water levels at the beach are correlated with the Gulf Stream position, especially in North Carolina, because you're taking a huge amount of water that also is a meter hill, and you're moving it in and out, right? And so it could affect water levels at the beach.
Online.
Oh, wait,
Check
yeah,
for
let me take a
online.
question online, maybe?
Messages right now. Yes. Am I supposed to say something?
In the meantime, we can take another question if you want. Anybody else?
I'm having trouble with
Wait,
geography.
let me get the mic because there's a bunch of people watching that can't hear you.
Would you explain the geography? I don't quite know where I am when I'm looking at that.
Oh, sure. Yeah, I think I had a slide on here that kind of centered, but this is Cape Hatteras. This is basically North Carolina. Here's Virginia Beach. This is Cape Lookout. This is Cape Fear, and these are called isobaths. So this is in this picture, a 600-foot isobath. So this is basically where we go from the continental shelf sloping down into the deep ocean. And so when we get out here, it's about 4,000, 4,700 meters deep. When we're up here on this edge, we usually define the edge I did earlier at 100 meters.
What are these bodies of water? Those two big indentions? I don't know.
Here?
Yeah, there and there.
Yeah, so
Where's
that's
Where am I?
so sorry. Well, I started the talk with this, but I'll tell you, this is a sea surface temperature image. So this is the temperature of the surface of the ocean at one point in time. And this water right here is called the Mid-Atlantic Bight water, which is cooler and fresher. And this water down here is the South Atlantic Bight water, which is saltier and warmer. And this is the stream, the Gulf Stream.
And those indentations, are those lakes? What are they?
Oh, these?
Yes.
These are the sounds. This is the Albemarle Sound. This is the Pamlico Sound. This is the Currituck Sound.
And where is Skill Devil Hills?
Up here. We are in here,
Right there.
and Cape Hatteras is here.
Thank you.
You're welcome. So how do you want to do the questions online? You want to bring it up, or you want to pick one? Oh, okay.
So you're saying that's the Mid-Atlantic Bight, and that incorporates the Labrador, part of the Labrador Current as well?
That's a great question, actually. So, a frequent, perhaps misconception is that the Labrador Current is this cold bit of water coming down and hitting the Gulf Stream and going under the Gulf Stream right there, right? I hear that a lot. The Labrador Current is up in the Labrador Sea. Some of that water certainly makes its way around Massachusetts and gets mixed into this water here where it's cold, but this isn't just Labrador Sea water, it's lots of different water. And the reason we don't call this the Labrador Current down here is, this is my interpretation, is that a current tends to be something that's persistent. Like the Gulf Stream persists here all the time, it's not always in the same place. The Labrador Current persists in the Labrador Sea in a general flow. This Mid-Atlantic Bight water is always here. Sometimes it's moving south, sometimes it's moving north, right? Depends on what
It was retreating during the summertime, on some of your satellite images, it got really, really warm there.
Yeah, so the tricky thing when you're looking at it from a satellite image is that this might all look warm, and that's because in the summertime especially, the sun's heated up that surface layer. But this is called the cold pool because it's always there. So
it's underneath.
yeah, and one of the nasty things that you find out when you start scuba diving up north of Cape Hatteras is that you get out there and you're like, oh, the water's 78 degrees. This is going to be a great dive. And you go down about 20 feet and you're like, oh, wow, it's 50 degrees. Because it's there. And that's why it gets up well. And so, not to overstate this, but there's no absolute. So it'd be wrong to say there's no Labrador Sea water in there, right? Yeah. Another one back here.
You've been studying this for 10 plus years, I figure. Are there people doing the same thing off the coast of Florida and up in the Northeast also?
Jim, right?
Yeah.
Good to see you. Yes, there certainly are. Doing all sorts of things. So there are some of these coastal ocean radars in Florida. People are really interested in the flow through the Florida Straits because it's kind of where the Gulf Stream starts, if there is a beginning to it. There are lots of folks studying these things all over the place. One really interesting baseline observation that's been made in the Florida Straits is there's a telephone cable that's been on the bottom that goes from land on Florida to the Bahamas. And it's not being used anymore, but somebody was sharp enough to discover that when you're flowing salt water over a telephone cable like that, it induces an electric current in it. And the amount of water that you flow over there is directly proportional to the amount of electric current that's induced in that cable. And so from that, you can get a nice long time series of what the volume flow through the Florida Straits is from the Gulf Stream. And you start to get a baseline so you can say, is climate change affecting that volume flow? Does it change seasonally? What causes the change? When we see the winds change over here, does it change in here? So, yes. Bill.
I know we have a number of academic centers in North Carolina that study various questions and issues related to this. I wonder if you could help us understand what's the role of UNC Coastal Studies Institute in moving forward this discussion?
So, specific to this research or in general?
Yeah, it's specific to the work you do.
Oh, okay. So, specific to the physical oceanographic stuff that I've talked about today, I think that the Coastal Studies Institute is becoming the epicenter for making these observations because of our proximity and knowledge about the environment out here. So when Woods Hole wants to come put a mooring out here, they say, well, you guys know what's going on out there. Tell us what you think we should do with it. What are the fishing regulations I've heard, right? Should I put something there, or is it going to get entangled? And so I think we're not there yet, but we are becoming an epicenter for research in this area for these measurements. And that's evident because of, I think, the regional locations of my colleagues, Woods Hole, NC State, UNC, Skidaway Institute for Oceanography in Georgia, right? All these folks are interested because it's an interesting area, and we have this nice facility that they can use to work here.
Yeah, I mean, NOAA and our recent collaboration with them, 2 weeks ago?
Yeah, so that big, I'm sorry for doing this to you guys. And that's a good example. Did I go past? Sorry, I did pass it. It's down here. So this buoy is actually a NOAA buoy, and a colleague of mine that I've known for years in NOAA called me up and said, hey, we want to test a buoy in very deep water in a real high current environment, and I know you guys do work in the Gulf Stream and you've done some deployments. Would you be interested in helping us do that? And I said, well, gee, our ADCP that's out there doesn't measure the surface currents. It's sitting on the bottom. So I'd love to have something in that same location that measures the surface currents, the top 100 meters. So if you guys are willing to deploy it there and give us the information, we'll help you do this. So that's what we did. Yeah, so it's fun to work with all the different groups of folks, for sure. It's productive. Ellie, do you have another question?
When you put the buoy out,
with the thing right there, does the buoy sink too?
It does. And it's pretty exciting because these train wheels, we do this backwards. So we put this floating buoy out and we put it behind the boat, we put the boat in gear, and we trail it off behind the boat on a cable. And then when we're ready, we lift these train wheels weigh about 2,500 pounds. We lift them up on a sled and we just slide them off the back of the boat. And they're sinking about 1,000 feet deep. So what you see is they go bloop and they're gone. And then everybody looks back 100 meters at the buoy and says, it's not really doing anything. And then all of a sudden this buoy starts trucking it through the water for a while and then goes down. So it's pretty exciting, yeah. Good question, Al.
One more question. For the fishing rod, what does the orange thing on it measure anything?
Yeah, it does. So this is our inexpensive way of making what I called CTD casts. So this thing measures the conductivity and the temperature and the depth of the water that it's in. So what we do is we pull up in an area that we think is interesting. One example is where we've had this thing on the bottom now for 3 years. We'd like to know what the water looks like above it, what different types of water are above it. So we'll stop right at that location and we just drop this overboard and it goes and it comes back up and we get a cast of what the temperature and salinity of the water is. And we haven't had it attacked by a shark yet. I say yet, but that big red glider has been attacked twice now off of Cape Hatteras and been debilitated to where we have to go rescue it. So maybe they should change colors, I don't know. Anybody else?
Well, just a silly question, but if the buoy goes down, how do you locate it to get the equipment back?
Oh, that's actually not a silly question. We had some discussion about that. So we drop those train wheels and we have someone standing right over them with a GPS, so we get a latitude and longitude of the train wheels. And it's not perfect because we're dropping in the Gulf Stream, so obviously it's probably kiting with the buoy and everything else, but we get in the vicinity. We have some instruments that aren't scientific instruments, but we put one on this called a pinger. And I can go interrogate that pinger when I'm ready to go get this thing back with a gun. I can put it in the water and it'll talk and it'll say, I'm 300 meters away over here. And then we can kind of zero in on where it is. And when it's ready to come back, again, for the reason that it's not really scientific instrumentation, the way this mooring works is the train wheels are on the bottom and there's a chain and then there's an acoustic release. And so this is an acoustic release for this pod. It works differently. But all that thing does for $6,500 is I talk to it and say, hey, are you down there? And it says, yes, I am. I'm 120 meters away. And I say, okay, let go of those train wheels. And I send it a signal and it goes, psh, and then that buoy floats up. And in this case, we send it a signal and it's supposed to let this ball pop out and all this line pays out to the surface. So this one's in only about 100 feet of water. And 9 months from now, when I go ping it, I want it to release this ball and let the ball pop up, and then I can pull it up on a line. These babies right here have about a 50% success rate, so we're used to diving on them. All right, thanks everybody. I appreciate you all coming out.